Hello everyone, today we are going to learn about vapor power cycle. Previously we have learned few of the gas power cycle. They are Otto cycle, diesel cycle and Brayton cycle. They are basically a heat engine for most of the mobile applications. So vapor power cycle, what are the applications for this cycle? For the old day, they use a steam engine. I think in Sabah we still have a steam engine via the rails the train. And currently we use vapor power cycle as a power plant to generate an electricity for us. So which is stationary application. So let's have a look some of the list of the power stationary in Malaysia. So Manjung is one of the largest power station, okay, in Perak. So if you look at here, so combined gas or coal, and noted ST is steam turbine. Okay, so let me see. So if you see this, 4ST means they are using 4 steam turbine to generate 3,100 megawatt. Okay, so if you're interested, you can refer to this website to know more about this power plant. Manjung Unit 4 Perak, Malaysia. This is the power plant. Okay. This is the turbine house. This is the steam turbine. Okay. So this is the operating parameter of this steam plant. All right. So let's go back to this. So before we move, go into the Rankine cycle or vapor power cycles, let's recall back to the Carnot cycle. Carnot cycle, bear in mind that this is for gas. So if you remember 1 to 2 for the PV diagram, 1 to 2 is isentropic expansion. And you can think about turbine in this part. And 2 to 3 is heat rejection, or you can say it's a condensation. 3 to 4 is compressed isentropically. 4 to 1 is isothermal heat supply. Okay, so if you look at the TS diagram, there is a curve here. So which you should learn from your fundamental thermodynamics. So the TS diagram for vapor, right? Let me make it a bit bigger for you. Okay. This line is called for saturated liquid and dry saturated vapor. So this curve is called saturation curve. So you can also refer to 4.3 at page 93. The STOP textbook, yeah. So for this line, right, it's actually they are at constant pressure. Okay, so 1A, B, C, and CD, they are at the constant pressure. So AB is saturated liquid, which is at water or SF state. BC is wet region. Okay, so the pressure remain constant with temperature constant. Latent heat is added to convert liquid to vapor. CD is superheated region. So the pressure is still at the same pressure, but the pressure line is upwards as the entropy increase and as well as the temperature increase. So if you would like to find the the dryness fraction, then you have to refer to this equation. Okay, so we're back to this Carnot cycle. If we want to look for the work ratio, the area in the cycle, okay, over the gross work output. Okay, so in this case is 1234 over 12BA4. All right, so the efficiency is 1 minus QR over Q in, or when you simplify the equation, is equals to 1 minus temperature cold over temperature hot, which is T1 over T2. So for Carnot cycle using steam or wet vapor, so 4 to 1, okay, we look at again, 4 to 1 is Q in, isn't it? At this part, heat supply in constant temperature and pressure. So, which is true, right? Two to three is cooling at constant temperature. So imagine we are using steam or wet vapor. So we can convert the whole process into 4 to 1 is Q in, right? We can use the boiler to boil the steam. 1 to 2, which is 1 to 2 is expansion. We can use condenser, right? Or 1 to 2 is turbine. Turbine expansion, condensation, expansion isentropically. So at this part, we're using turbine. 2 to 3 is vapor condense. So we are using condenser. 3 to 4 is compression. So we can use compressor or pump in this case. So Rankine cycle. So if you look at this picture, this is the Carnot 1, 2, 3 to 5, this part. This is very hard to reach, to control. It is more convenient for the completion of condensation 2 to 3 and reach to the saturation curve. At point 3, this is at liquid condition. So this is easier to pump to the boiler at point 4. All right. Pump, so smaller dimension. So therefore we can use a smaller pump size, and thus we can save the cost as well. All right. At state 4, water is not at saturated temperature. Okay. So heat is supplied to change the water to saturated water. So we shift back to the saturated line. Okay, they are at the same pressure, but not at the constant temperature. All right. So at point 1, okay, 5 to 1 is Q in. So steam at inlet to the turbine. So this part is 5 to 1 is we can use boiler. So the steam at the inlet to the turbine, it could be wet, dry, saturated. So assume the process is steady flow. So we can use first law of thermodynamics. And for the boiler part, basically there's no work. It's Q in but no work. So we can use that as Q equals to the delta of enthalpy, H1 minus H4. Why H1? Okay, let's look at this. Okay, so because this is a expansion, so the hash 1 is definitely higher than hash 4. So we have this equation. So for the turbine, expansion is adiabatic. So adiabatic Q equals to 0. So therefore we have the work at turbine. So hash 2 minus hash 1. And remember that the entropy for the turbine is the same for the inlet and outlet. So condenser is 2 to 3. So what happened there is the heat rejected isothermally. So let's check again. 2 to 3. 2 to 3, yes, is a constant temperature. So at this part, we don't have work. So therefore, we have heat rejected at this equation. So after that, 3 to 4 is pump. So pump is or compression isentropic. So Q equals to 0. Okay, so we have work input to pump. This is the equation, H4 minus H3. When the boiler pressure is low, 3 to 4 is nearly 0. Okay, so network input for the gas is, so what is the network input? Let's check. If we look at this equation, the work is happen at the turbine and the compressor. Okay, 3 to 4. So we plug in the equation. Okay, this is our network input. And if the feed pump is neglected, so therefore, so if hash 3 minus hash 4, this feed pump is neglected, so we only refer to hash 1 minus hash 2. If consists of feed pump work but not include them, it's called as gross work output. So the Rankine cycle now is net work output over the Q in. Okay. So from equation 7, so where's our equation 7? The network output over the heat supply in the boiler. So we have the network, which including the feed pump. Okay. If this is the Rankine cycle efficiency, or we can use this way, right? To add the, okay, we can substitute the hash rate in equation 8. All right, so from this, using this part, if our feed pump as equation 4 equals to 0, so this is the work input to pump. Okay, this is called feed pump. So if that is 0, so we can have hash 1 minus hash 2 over hash 1 minus hash 3. If included the feed pump, it is necessary to evaluate the work 3 to 4. The work 3 to 4 is the pump, okay? Assume the liquid is incompressible. So if this is incompressible, so the specific volume is constant. The increased enthalpy, increase for isentropic compression. So this is the equation. So why delta H equals to specific volume plus changes of pressure is du equals to dH minus VdP. Okay, so they are equals to 0. So when you simplify it, okay, so you can get this equation. So the pump work input is H4 minus H3 as when you refer to equation 4. So then we can use specific volume P to represent the H. Okay, so we have equation number 10. The efficiency ratio is ideal cycle over the Rankine cycle. What that means? So actual expansion is irreversible for 1 to 2. Let's have a look. Okay, I can move it. 1 to 2 is actual isentropic is irreversible. Actual compression also irreversible. Okay, so I can move this here to here. It's easier for everyone to understand. Okay, for isentropic compression, if you still remember what we have learned, so this is the equation for the isentropic process. So it might bend slightly, okay? So, and then for the turbine, so the isentropic turbine efficiency is the actual, because when you bend, the length from 1 to, let's say 2A is shorter. So always remember the efficiency is not more than 1. So that's why we put the actual over the ideal. So for the compression is 3 to 4. We look at 3 to 4. So it normally is bend in a little bit. So when you look at the length, the 3 to 4S, the ideal one, is shorter. So therefore it's isentropic work over the actual work. The turbine efficiency is this one. The specific steam consumption, this is important. This is one of the criteria of performance in steam plant. Steam flow required to develop unit power output. Steam flow indicate the size of the plant. So how to find the specific steam consumption? You can refer to this equation. So the mass of the steam over the power output. If neglecting the feed pump work, so your summation of the work, the power is equals to H1 minus H2. Therefore, SSC is equals to 1 over H1 minus H2. So this one is in unit kg over kj. Rankine cycle with superheated. Okay. So, okay. Rankine cycle without superheated, steam is wet and dryness fraction X2 is lower. So if we look at this one without the reheating, so the X2 is very hard to control, right? So what we can do is we can try to heat up a little bit to superheat it before the turbine expansion. So in this case, it's easier for us to control 2 to 3. All right. Figure 4A, this is the 4A, and B represent the Rankine cycle with superheated. Heat is supplied in boiler and the temperature increased by superheated steam. T6 increased to T1 before sending to the turbine. In model plant, receiver is used to receive steam from other boiler and placed between boiler and turbine. So imagine that we have the boiler here, but in a plant we can have so many boiler, so we can receive them and put in a receiver before send to the turbine. Feed water varies, therefore storage of condensate is set between condenser and boiler feed pump. What's that means? So what this means that the feed water, there's a lot of as I mentioned that there are different input to the receiver, so therefore the feed water is various. So it's good to have a storage here to control the flow. So there are two types of storage. One is the surge tank, another one is hot wheel. In figure 4a, this is a hot wheel. Okay. What else? So what is the benefit of having the Rankine cycle with reheating? You can increase the work done. Do you still remember the work done is the surface area in the cycle? So if you compare to this one, this is much higher surface area. So thus is higher work done. Okay. And the dryness fraction is increased. So you are no longer need to use another way to control or remove the dryness of the at 2, okay? And the SSC is decreasing. So what is SSC? We have to go back here, all right? The specific steam consumption, okay? The efficiency increase as degree of superheated increase, all right? So why, if you look at the equation, so we have to look at the equation. Where is the equation? I think is this one. Okay, so when we look at this, degree of superheated. So which part is superheated? H1 to 2. So when H1 increase, everything increase, right? So therefore the efficiency increase when you're using the reheater. Okay, so this is the example. I will show you the example and the tutorial together. So just refer to your Facebook for that, for further information. And yeah, that's all for the Rankine cycle. So check out in my Facebook for further information. Thank you, everyone.